All right. Let's play with traffic lights. So here's a version of traffic light code that I came up with that actually seems to work. The basic idea was to view the system in terms of 6 states, based on the fact that each light, at any point in time, exactly one light will be green or exactly one light will be yellow. Okay, and there'll generally be 2 lights that are red, but there'll always be exactly one light that's green or one light that's yellow. And if you know, for example, that this light is green and a car appears over here, then our next state should be that this light becomes yellow, and our next state should be that this light becomes green. And if we know which of those 6 states we're in, we can define the color of all 9 lights. For example, if we're in the state where this light is green, then this light should be red, this should be red, right? So this thing's yellow and red should be off. This thing's green and yellow should be off. This green and yellow should be off. Red should be 1, red should be 1. And if we're in a state where this lane is supposed to be yellow, these lights are exactly the same as if this light was green, but on this direction, the east, we should have yellow equal to 1 and then green and red equal to 0. So I've coded that up into some Verilog code. So there's 6 states. Yeah, I can zoom. There's 6 states which I call, direction and color. So west green, south green, east green, west yellow, south yellow, east yellow. And then we can make a transition table, which we don't really need to use, but it helped me think this out. So my present state is, for example, west green. And suppose there's no cars anywhere, so W, south, east, those are my car sensors. So if we're in the west green state and there's no cars anywhere, we're just going to stay in the west green state. But if we're in the west green state and a car appears on the east, we're going to go to the west yellow state. In other words, this light is green, this is red, this is red, and a car appears over here, we should change to the state where this is yellow. And after that, we should change to the state where east is green. So I wrote this up with a next state and a next state, right? So this table describes the next 2 states of the system. If we're in west green and there's a car to the east, our next state is for west yellow, and the following state is east green. And similarly, if we're in west green and a car comes to the south and there's not a car to the east, our next state is still west yellow, but the following state will be south green. And if we're in west green and there's cars to both the south and the east, the next state for the system is west goes yellow, and then east goes green, because that east car gets priority. And there's other states. Okay, so here's the 4 cases where there's also a car on the west, right? And as you noticed in lab 3, the western input doesn't really affect anything, right? Whether west is 0 or west is 1, we get the same behavior of the system, right? This is because west has the lowest priority. But I've written this out exhaustively, so it's a fairly long transition table, right, for each of your 6 possible states. And your 3 inputs, what's the next state, what's the next state. I actually didn't write any states for where you're in the yellow light, because those are all covered by this next state, right? The yellow light is a transitory state. Anyway, this is the full transition table, but we don't really need to worry about that. That was sort of part of figuring out the code. But here's the actual Verilog. So there's a clock input, there's a reset input, there's 3 car sensors, there's 9 light outputs. And so I didn't have to constantly say west green, south green, east green, right? I set these up to be parameter values. Okay, so 6 states, we've got 3 flip-flops, right? So my state is represented by 3 flip-flops. My next state is represented by 3 flip-flops. And I'm going to be able to use the symbol WG, for example, and that'll just mean the value 1. Okay, this is an arbitrary mapping. It's our state assignment table. When we're in state WG, it means our flip-flops are set to 0, 0, 1. When we're in state EY, it means our flip-flops are set to 1, 1, 0, right, is 6. We can change this assignment. It doesn't change the behavior of the system. It's triggered on the positive edge of the clock, and this would be the clock coming from our 555, so it's a 2-second interval from one tick to another. And if the reset line is asserted, oh, I shouldn't have double-clicked. I know that, but I do it out of habit. Double clicks also crash my my program. Double clicks in source code. Alright, so if the reset signal is asserted, we just go to state 1. Okay, and state 1 is west green. So if nobody's around, we're going to give west a green light. So that's our starting condition. Okay, otherwise, so I use a case statement. A case statement is like in C, it's just a way to write a bunch of if-thens. So this case statement basically says, if state is equal to west green, do all of this stuff. If state is equal to south green, do all of that stuff. Okay, so here's the simplified version of how the system moves from one state to another. If we are in the west green state, the only thing we have to know is there a car to the east or the south? If there is, our new state is going to be west yellow. And the state after that is going to be either east green or south green, depending on whether there's a car to the east. Okay, that's the whole totality of how the system changes state if you're in the west green state. If there's a car that has priority over you, either east or south, the next state's going to be yellow for west, and the following state will be green for either east or south. If we're in the south green state, and a car is sitting on the east, then our next state's going to be south yellow, and the following state will be east green. Otherwise, if we're in the south green state and there's a car to the west and there's not a car to the south, right, then we want our next state to be south yellow, and the following state will be west green. Right, so that's the case where we've got a green light here, everything else is red. And a car has shown up over here, and there's not a car sitting here. So now this lane has a car. We're going to change this to yellow, and then after that we'll change this to green. And then east green basically says if there's no longer a car on the east and there's a car to either the west or the south, our next state is east goes yellow. We're going to take away east's priority, and the following state will be either west is green or south is green, depending on whether there's a car to the south. If there's not a car to the south, the following state will be west green. Otherwise, it's going to be south green. And if we're in a yellow state, the new state's going to be whatever this next state was that we saved up here. And that's it. That's the whole state transition. So if we write out, the state assignment table and we start, making truth tables and K-maps and things like that, we're going to get a really complex circuit. But behaviorally, we can describe what we want our system to do with just a few statements of Verilog, right? And this is really derived from, starting with a human notion of what do we want the system to do if we're in a state where the green lane the east lane has a green light, right? What's going to cause that to change? Well, if a car shows up on west or south and there's not a car sitting on east, we're going to go to a different state. What state? Well, we'll go to first where the eastern lane is yellow, and then we'll go to either west or south being green. All right, so these things happen when the clock ticks, and they define which of the 6 states our system is in, and now we just have to set up the 9 outputs based on those states. Well, west green is equal to 1 if our state is west green, otherwise it's equal to 0. West yellow is equal to 1 if we're in state west yellow, otherwise it's equal to 0. West red is a little more complicated. If we're not in west green and we're not in west yellow, then west red should be 1. Otherwise it's equal to 0. And it's exactly the same for the other 2 lanes. And so that's it. It's 145 lines, but 79 of them are comments. So it's actually not that much code. So this should compile. Let's do our new waveform. Initialize our simulation. I'm going to drag all of this into here. So I'm going to set our clock at 25 nanoseconds. I'm going to set our reset to a hotkey, so when I press the letter R, it's going to toggle the value of the reset line. Actually, you know what? I'm going to change that to a formula. I like the way the formula worked before. So let's set it to a 1 in the beginning, and let's set it to a 0 after 50 nanoseconds. Alright, and then east, south, and west, I'm going to trigger those with hotkeys. So I can just press E, W, or S, and it'll toggle the value. Okay, so it'll let me control the behavior of cars arriving and leaving the intersection. And so let's start running this. And let me set my west to 0, let me set my south to 0, let me set my east to 0. And when I'm clicking these hotkeys, it's generating these simulation commands which say, set east equal to 0. So let's go ahead and run this. So our system is ticking away. And so west green, yellow, red, south green, yellow, red, east green, yellow, red. Let me do some color coding on these. So I'm going to pick these, and I'm going to come over here, and I'm going to say, let's make all of these signals green. And I'm going to go on the yellows. I'm going to say, let's make those yellow. And those are really hard to read. That's okay. And we'll make the reds red. If we can find a better yellow color. All right, so our system is running, and let's bring a car onto the west. So right now, west seems to have a green light. Okay, so let's bring a car to the south. So I'll hit the S button, and let's step the simulation. And you can see that west went from green to yellow to red, and when it went red, south turned on its green. And now let's bring a car to the west and step the simulation some more, and nothing has changed because south has priority. And there's still a car sitting to the south. That's what this upward trace here shows. So let's toggle S, have the car to the south leave, and you can see that when that car left, the next clock tick, let's see, south left, the next clock tick, the southern light, the green turned off, the yellow turned on, and then the next clock tick, the southern yellow turned off, red turned on, and at that point the green light went on the west, which has priority. And now if an eastern car shows up, we'll see that the southern light changes to yellow and then to red, and after it's red, the green light on the east goes up. And so now east has priority again. So you know, with software like this, you can write Verilog, you can verify it, you can debug it. My state variable is up here, and you know, I can click somewhere and see the numeric value of the state, or I can expand this and see the individual values of the 3 bits that make up the state. The next state I can read in here also, or I can collapse those, or I can delete them from the display if I don't care about them at all, right? So it's a pretty cool tool, right? And you can print these things. There's a print waveform option. I could save them to a PDF file, and then I could include them in a report, and so on and so forth. You can control whether you want the output to appear in color or black and white, and you know, set up different parameters on it. And so this is the thing where, you know, you get a piece of software to work with the stuff, you want to mess around with it, right? Sometimes you need to read documentation to get going on stuff, but more often than not, what you really want to do is just get your hands dirty, right? Roll up your sleeves and start playing, and figure out what you can do. And then if there's something you want to do and you can't figure out how, then you start looking for documentation, or maybe looking online. But if every time that you have a problem you try to find the solution online, you're not going to learn the peculiarities of this particular piece of software. And every piece of software has its own quirks, its own mindset, its own way of doing things. And it's only by working with it that you start to think the way the people who made the program were thinking, for better or worse, right? But this lets you be more efficient in working with the tool. And so whether you're using Eclipse or IntelliJ, Android Studio, MATLAB, Arduino IDE, Aldec HDL design tool, Xilinx ISE, you know, everybody has their own interface, their own set of software, and they're all a little different, sometimes very different. You get the big bucks when you can walk into a shop and you can start working with the software that they use and being productive, right? And so the ability to take a new platform, a new piece of software, a new set of tools, and get yourself up to speed pretty quickly, that's a really powerful thing, right? And as you work with different systems throughout school and throughout different jobs, right, you get better and better at that. That's a really good goal, right? You get sort of fluent in these different environments and get good at becoming fluent in them, right? So, and mostly it's mess around, you know. and you'll break stuff a lot, and you'll do things that make no sense, and you'll have to restart again. And you know, you get good at that too. I mean, you've seen how many times this software crashes for me, and I've gotten pretty good at getting back to where I was. I'm saving my stuff frequently. I know I can open a recent workspace, but not a direct workspace. So don't be afraid to jump in there and mess with tools like this. Alright, so that's a kind of large state-based system. And I didn't do any of the stuff that we talked about last time as far as, you know, using the LDEC tool to design a state machine by making a transition diagram and drawing arrows and stuff. I sort of circumvented that whole set of steps and just worked with this directly. So let's take a look at Lab 7 and see what there is to say on this. So question 2 should be pretty doable based on the homework question where you're implementing a down counter and the solved version where you implement an up counter. The difference here is your counter should be counting up or down depending on an input. So instead of saying, you know, count equals count plus 1 or count equals count minus 1, you can do something like if direction equals 1, then count equals count plus 1, else count equals count minus 1. Or maybe if reset equals 1, count equals 0, else if direction is 1, count equals count plus 1, else count equals count minus 1. Right, so you can modulate what you did in the homework question with the counter to get this. Experiment 1, I'm happy to talk about because people who have asked me about it, I've already told them this, so I'm not giving away secrets for people who haven't turned this in yet. But an 8-bit even parity generator. So you know, here's an 8-bit number. What does an even parity generator do? It counts the number of ones. Okay. We'll accept 8-bit data and outputs of 1 if there are an even number of ones. Okay, so 1, 2, 3, 4, 5 ones. So number of ones 5. Is it an even number? No. So what's our output? Should be a 0. Here's a different number. It has 6 ones. That is an even number. Our output should be a 1. There's a bunch of ones. The number of ones is 8. That's an even number. The output should be 1. Here's a number with 7 ones. That's not an even number. The output should be 0. Here's a number that has no ones. 0 is an even number, so that should output a 1. Alright, so those are some representative examples. Now you could do this with 256 if statements, but that's a really hard way to do it. Right? We could say if your number is this, output a 0. If your number is that, output a 1. But we're looking for something more nuanced, right? So the hint that's in the text is to think about the Xor function. Okay? Xor has this interesting habit. If you do 0 and you Xor a 0, you get a 0. If you do a 1 and a 0 or a 0 and a 1, you get a 1. But if you do 2 1s and you XOR them, you get back to a 0. So with just 2 bits, this tells us whether we have an odd number of 1s. And it turns out if we do 3 bits, this would give us a 0. This would give us a 1. This would give us a 1. The XOR of 3 bits tells us whether we have an odd number of 1s. So if we were to take 8 bits and XOR them, The result of that will be 1 if we have an odd number of 1s. Well, if we complement that, the result will be 1 if we have an even number of 1s. So if you have your circuit with 8 inputs, let's just call it A, B, C, D, E, F, G, H, and some output X, right? You can XOR all 8 of your bits, complement the result, assign that to your output. That'll give you your parity generator. But again, that's kind of a trick, right? That might work great if you know the XOR trick, and it's an efficient way to do it. But if you don't feel good about that, what if we just count the number of 1s and see if it's even? Well, how can we count the number of 1s in this number, or this number, or this number? How about if we just add them together? So number of 1s is going to have to be a 3-bit number, actually a 4-bit number, because it's going to have to count from 0 to 8. But if we just say add these 8 bits together and save that in this register called number of 1s, that's the number of 1s. That's this column right here. And then if we look at the least significant bit of this number of 1s, that'll be 0 if the number is even, it'll be 1 if it's odd. And so if we complement it, this expression here will be 0 if the number of 1s was odd, right, like here, and it'll be 1 if the number of 1s was even, like here. So this is just the least significant bit of that sum complemented. Yeah, if it has a remainder. So you could divide by 2, and if it has a remainder, it's odd, correct. The easy way to divide a number by 2 is to just shift the bits over one spot. We'll talk about this in 270. And the remainder is always guaranteed to be whatever that least significant bit is. So if I want to look at the number 5 divided by 2, it's going to be this, and that's going to be the remainder. And that works for any number written in binary. If I take this number and I divide it by 2, I'm going to get this, and the remainder is going to be 0. So that least significant bit is the remainder, which means it tells you whether the number is even or odd. If it's 1, it's odd. If it's 0, it's even. So that's a useful observation, and like I say, that'll come up in Engineering 270. We'll play around with that a fair amount. All right, shift registers we talked about a little bit already. Make an always block, and inside there basically assign each bit to the next variable. So if you want a 4-bit shift register, right, this synthesizes to an input going into a flip-flop, going into another flip-flop, right, where this is what we call D, this is C, this is B, and this is A. So when the clock ticks, right, tie all your clocks together.
Can't see the paper.
Thank you. All right, when the clock ticks, copy B to A, C to B, D to C, copy your input to D, right? So it synthesizes to a set of flip-flops. Input goes into here. This flip-flop's output is called D. The current value of that goes into this flip-flop whose output is called C. The current value of that goes into this flip-flop whose output is called B. And the current value of B goes into this flip-flop whose output is called A. Okay, that's the shift register. And every time the clock ticks, the input value will go into here. What was here goes there. What was here goes there. What was here goes there. And what was here is lost, right? It gets shifted off the end of the earth. So you can expand this to a 16-bit number, right? 16 variables. And there's your 16-bit shift register. So we can go through this in more detail Thursday. Like I say, some people haven't turned in the lab yet, so I don't want to do the full Verilog code for these. But we can do it Thursday, or catch me in my office before then if you want to go over it. And then same for the 5 of 6 event detector. But once you have a shift register, all you need to know is are there exactly 5 flip-flops whose value are equal to 1? And an easy way to tell that is just add up the values of your 16 flip-flops. If that sum equals 5, then you should output 1. So that's an assign statement, right? Assign output equals, A plus B plus C plus blah 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 equals 5, question mark 1:0. All right. We talk about subtraction. Have we built a subtractor yet in this class?
No, not that I remember.
I don't think we have either. So if we want to do A minus B, that's A plus negative B, right? This is a homework question. This was a question on the midterm, right? How do we do A minus B? Take the 2's complement of B and add it to A. So suppose we have an adder. Could be a 2-bit adder, could be an 8-bit adder. And it has 2 numbers coming in, A and B, so the slash means these are buses. It's a collection of lines. And it has an output, which is a sum. Okay, we can build a subtractor the same way we built an adder. We can make a half subtractor and a full subtractor and tie them together, and we can have a borrow instead of a carry, and so on and so forth. But it turns out if we have an adder, we can use that to do subtraction. If we could somehow take the 2's complement of B and feed that into our adder, this sum would be A minus B. Well, how do we get the 2's complement of a number? So the first way we learned to do this was take your number, toggle all of the bits, add 1. Okay, toggle all of the bits and then add 1. That's our 2 key steps. Well, another use for XORs is that XORs will sometimes toggle the value of a bit for us. So let's just think about a plain old 2-bit XOR like that. Let's look at this in 2 halves. Suppose that A is equal to 0. This output is exactly the same as B. So if A equals 0, then A XOR B is exactly the same as B. If A is equal to 1, the XOR is the opposite of B. So another way to view an XOR is it's a selectable inverter. It's an inverter we can turn on or off by using this A input. We can say if A is 1, I want to invert B. If A is 0, I don't want to invert B. So what we could do over here is we could take our B input and we could put it into an exclusive OR. And we can put an XOR with this, which we call add. And the idea is if add equals 1, then we're going to do addition. If add equals 0, we're going to do subtraction. Well, that's not quite right. Right? Because if I want to do subtraction, I need to get a 2's complement. I need to toggle all of my bits on B. So, and if I set this to a 1, it's going to toggle my bits. If I set it to a 0, it's not going to toggle my bits. So let's put an inverter in here. So now if I make this add signal 1, I have a 0 going into my XOR, and 0 XORed with B is just B. So if add is 1, what I have coming into my B input is just B. But if add is 0, right, that gets toggled to a 1, and 1 XORed with B is going to give me the opposite of B. So I'm going to have B bar going into my adder. So by flipping this one signal here to be a 1 or a 0, I can control whether I have the true value of B going in here or the complemented value of B. Alright, so I can complement my value of B, but I also need to add 1 to get the 2's complement. So what I want to do is if my add signal is equal to 0, I want to add 1 more to this complemented B. Well, suppose I build my original adder with all full adders instead of using a half adder for this least significant bit, so that I still have a carry in going into this first bit position. So I can take this signal here and I can feed that to the carry in. And if I do that and I set my add signal to a 0, I now have a 1 going into that original carry. And what is this sum? This is now A plus the complement of B plus 1. And this is negative B. So by setting my add to a 0, this subtracts A minus B. And if I set my add signal to 1, the output of this inverter is a 0. The output of the XOR with B is just B, and the carry in is a 0. This is just a plain old adder, and the sum is just A plus B. So that's one way to build an add-subtract circuit from just an adder. And the only trick is we need our adder to be able to accept an initial incoming carry. So this first stage here would be a full adder instead of a half adder. So think about that, ask questions if it's not making sense. But it's this idea that we can kind of do the sorts of things we do when we write software, when in fact we're designing hardware. We can think of modules that we can reuse or use in different ways to do different functions. All right, so lots more we could say on that topic, but let's leave it there for now. So catch me in office hours if you like, and if there's still questions on Lab 7 on Thursday, bring those to class and we can work out as many of those as we want in as much detail as people want. And I will post a sort of list of topics that we've gone over that you should think about for the final. And we'll talk about those on Thursday. So bring questions, and we'll talk about logistics for the final as well. I haven't written it yet. I haven't decided exactly what the final is going to look like, but I'll make decisions about that, and then we'll talk about the details of how we'll actually do the final. All right, that's all I got for us today. When will Lab 7 be officially due now? Is officially due on the original due date. Labs are allowed to be turned in late. It's normally 20 points a day deduction, but I'm being a little relaxed about that. But it was technically due last night. So, but I'm not going to take anything after Thursday's start of class. So make sure you get everything turned in by then. Does that make sense? All right, cool. I will catch you all next time. Have a great rest of the day.